Okay, we talked about two really important functions, the linear function and the quadratic function. But there's lots of other functions that we should recognise. So let's go now to the cubic. So we've got linear, quadratic. So a cubic is two different basic shapes a cubic can take. Now the classic one that we're used to seeing, like y equals x cubed over there, is the one that has what we call a horizontal point of inflection. And that just means that when it changes concavity, because you notice how it goes from concave down to concave up, at that point, if you were to draw a tangent in, it would be horizontal. So that's why we call it a horizontal point of inflection. And all of those types can be factorised down to be a perfect cube. Now, it might be a multiple of a perfect cube, but all of those can be done that way. The other type are ones that look like that. Okay? So it's still a continuous curve, but it has two what we call turning points. There's a maximum one and a minimum one, and in the middle there's still an inflection point, but if we were to draw a tangent there, it wouldn't be horizontal. It's going to be at some angle. So they're the two shapes that a cubic could take. And just like the linear function, just like the quadratic function, we can build every single cubic out of these functions. Might be rotation, might be translation, could be any of those. Could be a combination of them all. How do you recognise it? So similar to the others, now we're looking for the highest power of 3. So in this one I've got there, the y is to the power of 1, the x is to the power of 3, the highest power is 3. So we know we have a cubic function there, so it'll take on one of these two shapes. Polynomials in general then. So we start at power 1 linear function, power 2 quadratic function, power 3 cubic function. So polynomials, look, there's lots of different shapes as the powers start going higher that they can take. But anything that can be factorised down to a perfect whatever the power is. Okay, so that's the one that I'm interested in at the moment. We'll take on, well, if it's an even power, it'll have a U shape. Just like the parabola is to the power of 2, it has a U shape. Now, only the power of 2 is a parabola. The others are U shaped, but they're not parabolas. But what happens is, as the power gets bigger and bigger, then the shape gets steeper at the sides and shallower at the base. So I've sort of tried to exaggerate that a bit with my diagram there to illustrate how the base is a lot flatter and the sides are a bit steeper. And the same with odd ones, it will take the basic shape that, our basic cubic is. So any odd power. But again, higher the power, deeper at the sides, shallow at the base, and I think I've really exaggerated that one because it even looks flat at the base there. I might have overdone it a bit with my picture there. But that's the idea. It'll always take that sort of shape. Now, any other polynomial function will look like up and down, up and down, up and down, depending on the function as to how many turning points it might have. Recognising the polynomial function. So, all the powers will be integers. And the highest power tells us what type of polynomial it is. Not only integers, I'm glad I just looked at what we've got there, they have to be positive integers. So if it's the power of -1 or -2, that's not a polynomial. We say the degree of a polynomial is whatever that highest power is. So our quadratic is of degree 2, cubic degree 3, and so on. Linear function, for that matter, degree 1. It's a polynomial of degree 1. In fact, a constant number is a polynomial, but it's of degree 0. So sketching polynomials. Things to look for. Well, just like all the other shapes, the y-intercept's very easy to find. Sub in x equals 0. It's going to be the constant number. So let's use this as an example. Now, I don't have to expand the whole thing out to work out the constant. Because if I was, I would get all these constants times each other. It's the only way I can get the constant. So I know I'm going to have 1 times -1 cubed. So I'm up to, what's that? 1 times -1 cubed is. So we're at -1. But that'll be times 2 squared. So we're at -4. Okay, let's plot that in. So we know the y-intercept's -4. The x-intercepts are the solutions to the equation, the roots of the polynomial. And nicely, this has already been factorised for me, so I can solve that quite easily. We're going to have -1, +1, and -2. Now, out at infinity, plus or minus infinity, a polynomial will act like the leading term, so the highest power. if I was to ask you just to draw that shape, where would you start, where would you finish? And this one will do the same. So R1, again, I don't have to expand the whole thing out. To work out the leading term, I just multiply all the leading terms together. So I've got x times x cubed times x squared, which gives me x to the power of, what have I ended up with? 6. So if I was to ask you, draw x to the power of 6, well, we just saw even power. That's going to be a U shape. Is it concave up or concave down? Up, because it's positive. We have a happy one. So we know we start up there, and we finish over here. So we know where the curve starts and finishes. We've got some points that it goes through. The roots themselves behave like the factors. So if you've got a factor that's to a power of 2 or 4 or 6, any even power, it'll act like a U shape. So it'll just touch the axis. So in our one, at -2, we can see x plus 2 squared. So I know at -2 it's going to act like a U shape, but I also know it starts up there, so it must come down and turn at that point, okay? Well, the same thing happens with the odd ones, other than power of 1, of course, because power of 1, it would act like a straight line. It'll just cut straight through. But if it's an odd power, it's going to have that horizontal point of inflection as it goes through, like the cubic. So our one, yes, in fact, we have got a cubic. So at 1, it's going to look like a cubic, but I know it finishes up there, so you must come through like that. At -1, as I say, it'll cut through like a straight line. And in fact, that's what that one looks like. Now, where exactly it turns? Well, at this stage, we're just drawing rough sketches. Once we've done a bit of calculus, we could locate those turning points exactly. No, right, this is where the shape's going to go. But we can at least get a feel for it. We know what the basic shape of this polynomial will look like. All right, so that's polynomials. Circles then. And you may recall a circle, x squared plus y squared equals the radius squared. Now this is the one where we have to make sure we've got the same scale on both axes, otherwise our circle's going to get distorted. If we want a perfect circle, like the one on the wall, circles are not functions. It fails the vertical line test. They're actually made up of 2 semicircular functions. And so the top half is the positive square root, bottom half the negative square root. How do you recognise it? Well, now both of the pronumerals are to the power of 2, not just one of them. But more than that, the coefficients have to be the same. Now in this case, they're both 1, that's fine. If I had 2x squared plus 2x squared, still okay. If they were different, if I had x squared plus say 2y squared, I'm not going to get a circle. What shape do you think I'm going to get? If I don't have a perfect circle, what am I going to have? An oval, or let's give it its mathematical name, ellipse. An ellipse. Here's an interesting question though, do you know this one? If one's positive and one's negative, what shape do you get? So say I had x squared minus y squared there, or x squared minus 2y squared, doesn't matter. One's positive, one's negative. Any idea what shape that would actually get when you draw it? Interesting to see if anyone knows this one. Oh, hang on. What do you reckon? It goes out. What do you mean by out? You are correct. So if you think of a circle as the shape's going in, if it's the one's negative, the shape goes out. It's actually a hyperbola. It's just not in that orientation. Imagine, turn your head 45 degrees. That would be the shape we're talking about. So that actually is what we would have. All right, so as I say, the coefficients are the same. That's important. Well, let's talk a bit about the square root ones then, because we said circle is made up of 2 halves, often created when the independent variable is made the subject of the formula. So here we go. There it is, semicircle. And you could have a top half of a parabola. There's another classic one. So that one's y equals the square root of x. How do you recognise it? Well, you see a square root sign's a bit of a giveaway. All right. So if you're unsure what the shape's going to look like though, so say you get given y equals the square root of x, or y equals the square root of r squared minus x squared, and you're unsure, square it and let's see what happens. So there it is, the semicircle, square root of r squared minus x squared. I'm not sure, so I'm going to square it. If I square it and rearrange it, it's my circle. But because I'm talking about the square root, I've only got half the circle. And positive would be the top half, negative the bottom half. Our parabola on its side here, y equals square root of x. I'm not sure, so I'll square it. y squared equals x. Ah, that's a parabola on its side. But I'm talking about the top half because it's the positive square root. So that's how you can recognise the shape if you're not sure. Positive square root, as I say, top half. Negative square root, bottom half. Okay, 3g